It's probably worth saying from the start that I'm a climate scientist rather than a climate change scientist, so I'm interested in the way the climate system works. And quite frankly, I'd be interested in the way the climate system works even if we weren't messing with it. The climate system is an interesting beast with lots of complex interactions that affects the way we live. But of course there's the backdrop of human influence on climate, which is a major motivation for me. So I would say that this doesn't represent what I research, but it's there in the background all the time. And we have Myles here, who of course is more closely tied to this in a research sense, if we get any really tricky questions. So that's great. Do feel free to stop me anytime. I'm quite happy to be interrupted. I'd rather things were clear, and especially as it's quite a diverse group, and it's possible I'll have made assumptions about what some of you know. Equally, I don't want to patronise you, so tell me if it's all old news, and I'll move on. Okay. My first slide is blatantly stolen from some of Myles's lecture notes, as are many. Those who sit in geography will perhaps know. But I think, for the people who are writing up the summary, this might be a good start. So you've got the same name, Climate Science 101, as your course handbook. Yes, global mean surface temperatures are warming. Yes, it's us. We're sure it's us. Hopefully I'll show you these things today. These are really significant changes that we're talking about in geological context, and then hopefully end on a bit more of a positive note about the prospects for fixing it in a purely scientific sense. Okay. So here's roughly where I'm going then. So the first third of the talk will be some basic climate physics. How do rising greenhouse gas concentrations cause warming? Then we'll have a section on global warming to date, try and show you how we know that human influence is the dominant cause of the recent warming over the last few decades. And then we'll move to the future and talk about what science suggests in terms of mitigation, what we expect and what science suggests we can do with it. So you have to bear with me here. I'm going to have one slide of pure physics, which I think is all the pure physics you really need to know to understand this problem, basic physics, and that's that the amount of radiative energy that anything emits, everything above absolute zero, above 0 Kelvin, is emitting radiative energy, and the amount of energy that thing emits and the wavelength at which it's emitted depends on temperature. And that's the key physics that underpins all of this. And so there's this graph over here. So we have intensity of radiation on the y-axis and wavelength on the x-axis. And each of the curved lines shows you the radiation, the energy emitted at a given temperature, and these are the temperatures in Kelvin. And you can see that as the temperature increases, not only do we emit more radiative energy, it also happens at a lower wavelength. Okay. And so if you understand that, then that's the key to understanding the greenhouse effect. The total amount of radiation emitted depends on a constant times temperature to the power of 4. Okay. Right, so moving on then. So the sun's surface temperature is about 6,000... Is this going to work on the screen? No. I'll point. The sun's surface temperature is about 6,000 Kelvin. So the sun emits radiation that's very much what we call shortwave radiation. So it occurs in the visible part of the electromagnetic spectrum. Is everyone familiar with an electromagnetic spectrum? Electromagnetic radiation, which spans very short wavelength waves, gamma rays, right through to long wavelength radio waves. And the sun emits in the visible part of the spectrum. That's no coincidence. We've adapted for our eyes to work in that part of the spectrum. And a little bit in the ultraviolet and a little bit in the infrared. Okay. And that's because of its temperature, where it sits on this curve. Okay. And the Earth is bathed in that radiation. Okay. And the Earth as a system absorbs much of that radiation. Some of it is reflected, a lot of it is absorbed. And the Earth, as a consequence, warms up. Okay. In order to reach an equilibrium, the Earth has to be emitting as much energy back to space as it's receiving from the sun. Okay. And so it warms up until it reaches a temperature where the radiation that it's emitted is the same as what's coming in from the sun. Okay. So sigma T to the 4, okay, warms up till sigma T to the 4 is equal to the radiation coming in. Okay. And we can work out the temperature that that it has to warm to do that, and that's 255 Kelvin, or about minus 18 degrees Celsius. Okay. So that's what we call the planetary emission temperature. Okay, that's the temperature that the planet has to be at to stay in equilibrium, or that the planet as a whole has to radiate energy at in order for us to stay in equilibrium. Now that's noticeably less than the surface temperature of the planet. Okay. And that's because the radiation that's emitted to space is not coming from the surface. Okay. It's coming from somewhere high up in the atmosphere. Okay? So to understand why the radiation that we see that's emitted to space from the Earth system is coming from high up in the atmosphere and not from the surface of the planet, you need to understand something about the atmosphere, and this is where greenhouse gases come in. So we've said that the solar radiation is emitted in the visible part of the spectrum. This is the electromagnetic spectrum, ultraviolet, visible and infrared radiation, so increasing energy as we go this way. So a warm body like the sun emits here, and a colder body like the Earth at 255 Kelvin emits in a very different part of that spectrum. Okay, it emits less radiation. That's not clear from these curves at the top here. They've been normalised so that we can see them together. There's a lot less radiation emitted by the Earth because it's much cooler than the sun, but it's also emitted at much longer wavelengths. So we talk about shortwave radiation emitted by the sun and long-wave radiation emitted by the Earth. And the important thing on this figure is this panel here, okay, which tells you the fraction of the radiation at each wavelength that's absorbed on a single pass through the atmosphere. So that might be shortwave radiation coming down, or it might be long-wave radiation coming up from the Earth. And it shows you how much is absorbed. And there's a few key things to notice. The first key thing to notice is that the atmosphere is really, really quite transparent in the visible part of the spectrum. Okay. So the sun's radiation is able to pass through the atmosphere relatively unhindered in the visible part of the spectrum. In the ultraviolet, the atmosphere is really opaque. Okay. So the sun's radiation in the ultraviolet part of the spectrum really doesn't get very far at all. And then in the infrared, the atmosphere has very variable opacity. At some wavelengths it's completely opaque to long-wave radiation, and in others it's completely transparent. Okay. The lines at the bottom show you what it is that's doing the dominant absorbing at the different wavelengths. And the first thing to notice about this is what's missing from this list. 78% of the atmosphere is nitrogen. That doesn't feature in this list. 20% of the atmosphere is oxygen. We're up to 98% now. And oxygen absorbs only in the ultraviolet down here, the solar ultraviolet light high up in the atmosphere. And so the dominant components of the atmosphere that make up 98% of the atmospheric composition play no role in this absorption of radiation at all. What's doing it is minor constituents in the atmosphere, trace gases if you like carbon dioxide, ozone, methane and water vapour. Okay. And these are what we call the greenhouse gases. Many of them are triatomic molecules. They've got 3 atoms in them, and that gives them rotational and vibrational modes that make it easy for them to be excited by infrared radiation. So they can vibrate faster, if you like. They can easily absorb, take on energy at infrared wavelengths. Okay. So that's just a summary of what I've said there. So what that means for the atmosphere, this is the a kind of recent steady state global and annual mean energy balance. The numbers here are in watts per metre squared, so energy per unit time and area. And what it means basically is that the incoming solar radiation from the sun, while some of it is reflected, okay, from clouds and from the Earth's surface, very little of it is actually absorbed by the atmosphere. Okay. The bit that is absorbed by oxygen very high in the atmosphere. In contrast, the radiation from the Earth's surface is almost all absorbed by the atmosphere, except for in very narrow wavelength bands, we call the atmospheric window. At most wavelengths, all of the energy emitted from the sun's surface is absorbed by the atmosphere in a relatively thin layer of the atmosphere, actually, and then re-emitted up and down, to be absorbed again by another layer of the atmosphere, re-emitted up and down, absorbed again by a higher layer of the atmosphere, such that the only radiation that can escape back into space is radiation that's emitted from so high up in the atmosphere that there's not much atmosphere above that level. There's not much greenhouse gases to actually do the absorbing above that level. The atmosphere gets thinner as you go up. We'll look at that in a second. And so as you get higher, there's less and less concentration of greenhouse gases, and eventually you get to an altitude where there's not enough greenhouse gas above you to reabsorb that radiation that's emitted, and that's where radiation escapes to space from. And that's the level where the temperature has to be 255 Kelvin. So as a consequence, when we look at the planets in the infrared wavelengths, what we see is something like this. Okay, we don't see the surface, we see somewhere several kilometres up in the atmosphere. And then just to go through this again and make this perhaps a little bit more rigorous, this graph has got two separate bits of information on it. One is the temperature structure in the atmosphere. So there's this height on the y-axis, and on the up here we've got temperature marks. And so as you go up through the atmosphere, through the lower 10 or 15 kilometres of the atmosphere, the temperature drops off linearly with height, okay, for good physical reasons that we understand. Okay. The other curves here show you the concentration of any absorber, any gas like CO2, above each particular altitude. So if you just focus on the dotted line for now, okay. So if we know that radiation can only escape to space from an altitude where there's sufficiently thin atmosphere above, okay, then we might say, okay, radiation can escape to space if we have less than 0.5 on this axis, and so it can escape to space when we get to a height of about 8 kilometres, okay. At that height, the temperature of the atmosphere is 255 Kelvin, minus 18 degrees C, okay. Is everyone okay with that? Provided the temperature at that height is 255 Kelvin, then the radiation emitted that's getting out to space is equal to the solar radiation that's coming in, and we have a balanced system. Okay. But what we do when we add carbon dioxide or other greenhouse gases to the atmosphere is we increase the concentration of the absorber throughout the whole atmosphere. So you can imagine stepping up to this dashed curve here. Okay. So it still decreases with height, but what it's done is it's pushed up the level from which radiation can escape to space. So if we're still looking for this tick here, I should have drawn some lines on here, then it's pushed up the level from which radiation can escape to space. So it's now happening at a higher altitude, and at that higher altitude, because of this decline in temperature with height, the temperature is colder. Okay. And if you remember, the amount of radiation that's emitted, sigma T to the 4, is now less because we're at a colder temperature. So we've got the same amount of solar radiation coming in, but our emission back to space from the planet as a whole is happening higher in the atmosphere where it's colder, and so there's less of it. And that gives us an imbalance, less outgoing radiation than we have solar radiation, net solar radiation coming in the bit after we've had some reflected. Okay. So what that means is that we've got more energy coming in than going out, and the planet is destined to warm. So I'm going to show you that slightly differently. This is another of Myles's lovely schematics. This graph shows you what happens to the height that radiation escapes to space from as we increase carbon dioxide in the atmosphere. And so there's a red line at the top that shows you the total amount of energy escaping to space, and there's you'll see some red lines appearing here that shows you the energy escaping to space from each level. And so as we increase carbon dioxide concentrations, you can see that the levels from which things are reaching space move up through the atmosphere and the total goes down. So to summarise again, high cold air radiates less energy to space, generating a surplus of incoming over outgoing radiation. This is what we call a radiative forcing. So I've summarised that there. I'll make the notes available so you've got that there.
Can we go back, Helen, to the way the spectra, just because it's this is a nice explanation to draw attention to one of the sort of sceptic arguments that's often thrown out. The one before then. No, one before then. There we go.
Yeah.
So I just wanted to sort of draw attention to something which people, if you look at this one, which people are often fond of pointing out, well, look, the water vapour is interrupting everything where the carbon dioxide is absorbing. Do you see? Where the carbon dioxide is doing its absorption, there's also a lot of absorption by water vapour. So this, if you go on blogs and ask, if you Google carbon dioxide, you'll find, Helen, we were just chatting beforehand, it's remarkable how quickly you get from sort of like normal useful information into complete garbage if you Google anything related to climate change.
Yeah.
Anyway, so one of the favourite lines is, well, the water vapour is absorbing everything, so it doesn't make any difference if we add more carbon dioxide, because it's opaque anyway. And if you look at that diagram, you see that it looks like there's something in there. But the reason for that is that this is looking at the whole depth of the atmosphere. But the story Helen's just told you is about what's going on up high in the atmosphere, which is well above where all the water vapour is. So, again, it's just one of those things where it's one of those lines of argument that people quite often like to throw around, just to sort of chuck a little bit of grit in the wheels and make you feel a bit confused about this. And it's not helped by the fact that actually the sort of conventional greenhouse analogy people get taught in schools is actually wrong, and so it sort of makes it easy to sort of mess around with people's understanding of the issue in this way.
Yeah. I think it's true that somewhere between 7 and 10 centimetres of water will absorb all the outgoing long wave radiation. So if you have, so first if you have a bag of water that's got 7 centimetres thickness of water in and you shine an infrared camera through it, you can't see the other side. That means if you've got cumulative 7 centimetres of water in your column of air above you, then that outgoing long wave radiation can't make it through, it's absorbed. Again, that's actually satisfied in the bottom a few kilometres of the atmosphere, usually. Yeah, but as Myles says, that doesn't change any of the argument for higher up in the atmosphere. I have a slide on the saturation argument in a minute. So, yeah.
So is water vapour trapping then? Is that
yes, water vapour is trapping as well. Yeah. Okay. Yeah. Okay. Right, let's carry on. Where did we get to? Okay, so we said that as we've lifted the level from which radiation is escaping to space, we've got less outgoing radiation than we have incoming radiation from the sun, and that's given us a positive radiative forcing, what we call a positive radiative forcing, so a surplus of energy which is going to warm the planet up. And that's going to continue until the temperature at the new emission level, if you like, is back at 255 Kelvin. So what we're emitting to space is again the same as what's coming in from the sun. And because the rate at which temperature changes through the lower part of the atmosphere, the lower 10 or 15 kilometres, is constant, and we know roughly what that is, in order for the temperature up here to increase, then the temperature at the surface has to increase too. Okay? Questions? No? Everyone happy? So this is making a point similar to Myles's point. So Felix suggested. No, it's fine. That's fine. That's fine. Thank you. No, please do dive in. So Felix suggested that we try and do a bit of debunking of myths as we go through, and so this, Myles has done one, and this is a similar argument that the atmosphere is saturated either with CO2 or water vapour or whatever you like in some wavelength bands, and adding additional CO2 won't really have any major impact. But hopefully you can see from my argument that there's always scope to push up that level at which the emission to space is happening, because the carbon dioxide concentrations are always going to fall off with altitude. They're dependent on the density of the atmosphere, which decreases exponentially as we go up in the atmosphere, and so it's certainly not saturated in that
What's
respect.
decreasing exponentially in the atmosphere? I just lost that part.
So lots of things, the density of the atmosphere, but also the concentration of all these gases that we're talking about, the carbon dioxide. Yeah. And because of this, exponential decrease in the concentration of the greenhouse gases and this linear decrease in temperature with height, then every doubling of CO2 has the same impact on the radiative forcing, this imbalance at the top of the atmosphere, as every other doubling of CO2. Okay, so wherever you start from, you double CO2, you have the same impact on the radiative forcing. And that's about 4 watts per metre squared, 3.7 watts per metre squared. That's relatively well pinned down. Okay. What's a lot less well pinned down is the amount by which the climate system will warm up. Okay. And that's due to feedbacks in the response. Okay. So as we start to increase greenhouse gas concentrations, we start to warm the planet, lots of other things change too, which also affect that radiation budget. So we've already talked a little bit about water vapour. Any physical scientists amongst you will know that a warmer atmosphere can hold more moisture, and so there's a feedback right away, right there. We also change the amount and the brightness of clouds, which change the reflectivity of the Earth, and consequently the amount of solar radiation that's reflected, and change the surface albedo, so the reflectivity of the surface itself. And also this rate at which temperature decreases with height, we've said that's relatively well known and fixed. It's possible that will change too. It's called the lapse rate, that will change too. And so there are feedbacks in the system which mean that while we know what to expect in terms of the imbalance in radiation at the top of the atmosphere, we don't know what to expect in terms of the surface temperature response, okay, even the global mean surface temperature response. And so what we call the equilibrium climate sensitivity, the long-term response to a doubling in carbon dioxide, after which you hold the concentrations of carbon dioxide constant for a long time. Estimates of climate sensitivity is quite a broad range, kind of 1.5 to 6 Kelvin, roughly. Here's the figure from the Intergovernmental Panel on Climate Change report in 2013. I know there's been other estimates since, but I don't think they changed the story particularly.
Well, there was an estimate published today in Nature, I believe. Or was it, what day of the week is it? Yes, it was today, which actually gave it sort of right down the middle, and I just thought it was quite amusing that this was headlined in the Times as alarmist predictions about climate change shown to be wrong, because of course this new estimate had trimmed down the top end of the range. It had also trimmed down by an equal amount the bottom end of the range, but for some reason the Times didn't report.
Okay, so it might be worth, you might think that we know how much carbon dioxide we've emitted into the atmosphere, and we know, roughly speaking, how much the planet has warmed. So one question is why we don't know the climate sensitivity. Why can't we just work it out from what's happened so far? And that is actually reasonably complicated answer to that, but the simple story is that there's a delayed response because the heat doesn't ultimately stay in the atmosphere. The extra heat in the Earth system, most of it ends up in the ocean, and transferring it into the deep ocean actually takes a long time. It's not to say that it takes a long time for the temperatures at the surface to change. It's maybe offset by other feedbacks, but it does make it difficult to estimate the climate sensitivity. We don't understand the details of the feedbacks enough, and how they interact with each other, and how much of the warming we should expect we've already encountered. And so it's estimating the climate sensitivity is a tricky thing to do. Okay, so what do we know then? So we know that atmospheric carbon dioxide concentrations are rising. So the latest value on the website that reports the Mauna Loa observations in Hawaii, so these are made at the top of a volcano in Hawaii, is 408 parts per million. You can see the time series here from the 60s. And we know what's causing that. Okay, we know it's not volcanoes. There's another myth debunked. Volcanoes produce more CO2 than the world's cars and industries combined. Volcanoes produce, I think it's less than 0.5 gigatons of carbon per year. We produce 10 gigatons of carbon per year at the moment. And you can't, as you look at the carbon dioxide concentrations increasing, you don't see any influence of these major volcanic eruptions in that time series of carbon dioxide. And so it's certainly not volcanoes.
I feel strongly about them because my 8-year-old kid came home from school and told me that. Oh yeah, Dad, no, I heard that actually. And I was like, if an 8-year-old is being told you this, I find that worrying. Anyway.
Very worrying. So where is it coming from? So it's coming from fossil fuel burning, as we all know. So this, using this pointer, which doesn't work. This breaks it down in terms of coal, oil, gas and cement, but mostly from what jumps out from this figure is the rapid increase, especially since the kind of 50s, 40s, 50s. You really see that huge steep curve. There's also a contribution that comes from land use change, shown in the yellow here. That's things like deforestation. And then on the bottom here, this shows you where that carbon dioxide ultimately ends up. So the previous graph was where the heat in the system ends up, but this is actually the carbon dioxide. Okay, and you can see that some of it goes into the ocean. You can see the dark blue portion here, and the green is parts that are ultimately locked up on land. But what's left in the atmosphere is about 50% of what we emit. So these carbon dioxide changes are large in the grand scheme of things. I sit in an earth sciences department. I work very much on kind of modern day processes, but I'm surrounded by people who worry about the much longer time frame. So this shows you the CO2 concentration in the atmosphere measured from bubbles in ice cores taken from the Greenland and Antarctic ice sheets over many glacial cycles. So during glacial periods it's cold and we have low carbon dioxide concentrations, 180, 200. During warm interglacials it's warm and we have 260, 280. So there's a range there of 100 or so over glacial cycles which take place over tens of thousands of years. You can see this goes back 800,000 years. And here's where we are today, up at 400. So we're well outside anything in this recent glacial interglacial cycle. We're also starting to look special in terms of the longer climate record. So here we are at 408, increasing quickly, and you can see that certainly when we get to kind of 500, 600, 700, we're it's starting to look like 20 million years ago that we know that we had carbon dioxide levels that high. The Earth's climate does vary on all time scales. It has long natural rhythms. We've seen some, the glacial interglacial cycles on the previous slide, and even longer rhythms, but we're certainly seeing something that's unusual in geological terms and is happening very quickly compared to geological changes.
And what would have been the geological cause for that, like that kind of similar level 20 million years ago? Would it have been just like the interglacial?
I don't know that far back. I'm more comfortable on the glacial interglacial cycles, but even there we don't understand. We can't. Oops, sorry, wrong way around. We can't fully explain this change of about 80 to 100 parts per million over the glacial interglacial cycle. We don't know. There are lots of contenders, but we don't know concretely what causes that change yet. And I'm not sure. Do you know about the longer time?
I think it's on the very long on the glacial cycles. Milankovitch cycles play a big role, but they're part of it. No, on these very long time scales, it's subduction into the Earth's crust, because that's the only place it can go and to store it away. And I think, this is where your colleagues would know, but I think the big transition sort of 30, whatever it is, 20 something years ago, was a reconfiguration of the continents, which meant that a lot of carbon which was in the atmosphere then got squirreled away down back into the Earth's crust. It's not the formation, it's not when the fossil carbon was formed, that was way before then, back in the Carboniferous. So that carbon got subducted down into the Earth's crust, I guess, in the form of submarine sediments.
Carbonates, yeah. So generally speaking, the carbon dioxide that comes from volcanoes into the atmosphere is balanced by carbon dioxide returning into the Earth's interior at subduction zones where the sea floor becomes subducted into the interior, and the sea floor often has a layer of carbonate sediments on it which contain a lot of that carbon, and that's in balance generally, but there are times when that balance changes.
The main theory for why the carbon dioxide concentration was so rapidly reduced about 30 million years ago was when India crashed into Eurasia and formed the Himalayas, and then you had a lot of fresh rock being made, which caused very rapid weathering of the rock, in which the carbon dioxide was incorporated into the rock. So it's something as big as the formation of the Himalayas.
But crashing makes it sound, I mean, you should bear in mind, this didn't happen overnight, and that's why it's so different from what's going on at the moment.
Yeah.
I mean, we are talking about that. I don't know how fast that crash happened, but it's a lot slower than what's going on right now.
Okay.
Sorry, one question about this graph. What is represented by the vertical width of the blue? Is that uncertainty or like physical fluctuation?
It's uncertainties, yeah. All of the vertical bars are uncertainties. I'm not sure actually what the blue is.
The blue's modelling, I believe, isn't it?
Yeah, okay. Doesn't say actually.
Okay, I think it's the GSX. I think that's a range of models of what's going on, but I don't know which models.
Obviously it gets less well pinned down as we go back in time. Okay, so carbon dioxide variations are not new for the planet, but but the changes in the recent century have been very significant.
And I think a change on this speed is new.
Yes.
I think it's very hard to imagine a mechanism that would make it change this fast.
Yeah. This is a graph I imagine many of you have seen before. So this takes the same record of carbon dioxide, now just over 450,000 years, and plots alongside it temperature change measured over that same period. So this temperature is measured using the oxygen isotopes in the water that's melted from the ice core data. So drill far enough down under Greenland, the ice at the bottom is really old, melt it and look at the oxygen atoms in the water molecules, and you can back out the temperature at which the temperature of the atmosphere when that water precipitated out. And it's quite an integral measure, so and you can see that the CO2 levels and temperature have been very closely coupled, at least over this record, and we have no reason to think that that didn't continue further back in time. Which is a large part of the evidence of the link between carbon dioxide and temperature, but it's not everything. So there's also direct evidence that recent changes in the greenhouse gases in the atmosphere are affecting the radiation budget. So this is a figure that shows the difference in outgoing long-wave radiation during two periods, in 1970 and 1997. There's a place in the mid-Pacific. So this is wavelength on the x-axis and brightness temperature up here. If you look at the difference, there's a difference in part because the planet has warmed over those 30 years. But if you take that away, then you can look at the change in the outgoing long-wave radiation just due to the composition of the atmosphere. And that's what's shown here. And you can see that in general, the brightness temperature is lower, and that's because the radiation is emitted from a level higher up in the atmosphere, remember, where the temperature is lower and consequently the radiation is smaller, the outgoing long-wave radiation is smaller. So lower by about 2 degrees up that temperature curve in the wavelengths that are affected by carbon dioxide. You can also see methane on here, ozone, some of the CFCs. So direct evidence that things we've put in the atmosphere have influenced the outgoing long-wave radiation. So it's not all about a paleo story of carbon dioxide and temperature. Okay, so given that evidence, why do we still need to explain the evidence for human influence on climate? Well, because of people like this. So Scott Pruitt is head of the US Environmental Protection Agency, and when asked the question, do you believe it's been proven that CO2 is the primary controller of the climate, replies, I would not agree that it's a primary contributor to the global warming that we see. And so people in immense positions of power and responsibility that still don't understand the problem. And so, so I'm going to lay out, following Myles's lead in his lectures, I'm going to lay out a very simple test, I guess, of the kind of null hypothesis that's implicit in this question, the idea that the recent warming has nothing at all to do with human emissions of carbon dioxide. And we're going to test that hypothesis and see if we can reject it. This is something that Myles, amongst others, have been doing for decades and continue to do regularly.
Evidently not very successful.
So everyone agrees the world has warmed since 1900. This is the first time.
Maybe not everyone, but at least Scott Pruitt does agree with that.
Most people, right?
No, I know, but you'll find nutters on the internet. But I mean, okay.
So there is uncertainty in how much, these numbers are not certain.
Everyone serious agrees. Even people who are moderately unserious,
Yeah. So there is uncertainty, I mean, joking aside, there is uncertainty in how much the world has warmed and in the details of this graph, but it's not, not enough to change the story significantly. We also know, I've just shown you some evidence for that human activities have been disturbing the global energy balance, this balance between incoming and outgoing radiation at the top of the atmosphere. You can see that here. This is the radiative forcing, if you like, the top of the atmosphere imbalance in orange, the human contribution to that. We also know that natural factors have also disturbed that balance over the last century. So both long and short-term solar variability, more and less radiation coming from the sun in the first place, shown in the green lines here. And then volcanic activity. Now, it may be confusing to look at this and to see that volcanoes actually look like from this, like they cool the climate. They have the opposite. We've just talked about volcanoes emitting carbon dioxide. Okay, volcanoes impact climate in two ways. They do emit carbon dioxide, largely balanced by that in subduction zones, as we've seen. But also they emit sulfate aerosols, which up in the stratosphere influence clouds and radiation. And the dominant effect is a short-term one that involves a negative radiative forcing. Okay, so we know the planet's warming, and we know that human and natural activities are modifying that top of the atmosphere balance. We also know that the climate system takes a while to respond to things, it conserves energy, and so things like these short volcanic events, our expected response to them is a little longer term. What we don't know is the magnitude of the response to these various forcings. I explained earlier that various feedbacks in the system mean that it's not clear exactly how the surface temperature responds to each of these different forcings. Okay, so it's just the shape of the curves here that you should be focused on at this stage. We can dial them up or down because we don't know what the constant, if you like, multiplying each of these forcings is. Okay, and so one way forward is to try and estimate them objectively from the data. Okay, so to try and work out. So, for example, we could multiply the solar forcings by 10 and take it up there. So to see if we allow, we don't understand the mechanisms by which this would happen, but if we allow the natural climate drivers to have a big response on the surface temperature and initially assume that human carbon dioxide emissions has no influence on the temperature, can we explain this temperature increase? So without recourse to the orange line initially, can we fit those data just using a kind of least squares fit? If you try and do that, allowing for any scaling of the volcanoes and the solar forcing, this is what you end up with as a kind of best fit explanation of the observed warming. And you can see that it's not terrible for the first part of the record. In fact, if you drew a line in 1980, maybe, you might say, oh, there's something in that. Maybe it is solar variation. But you can clearly see that, since 1980, the sun seems to have gone into a bit of a decline, and the surface temperatures have continued to rise. And so there's a lot of variability now that's not explained by this best fit line. What really makes it clear that we really do need to include some human-induced warming into the system is the residual. So the plotted in black here is the residual that's not, so the difference between the black curve and the red curve, okay, and it's plotted alongside what we expect from the human-induced warming. And you can see that the residual fit here looks very suspiciously like the human forcing. Okay, so it sort of takes off in the 1970s when CO2 emissions really take off. And so what we're going to do now is, shown by this little blue diamond here, is we're going to gradually dial up the amount of human influence warming we allow in this fit, and see if we can do a better job of explaining that observed temperature trend. Okay. So we start with about I'm not going to explain the units Myles chooses to use here.
True, it is 0.1 degrees.
Yeah.
I don't think anybody else uses this unit.
Good. I don't think we should dignify the name. Okay, so if we start with about 0.1 degrees of human-induced warming since the pre-industrial era, then we do slightly better, and you can see that as we increase up in 0.1 increments, you can see that not only do we fit a bit better, but the residual comes down. We keep going. By the time we get up to 1 degree of human-induced warming, you can see we've clearly gone too far. There's now a negative residual that's unexplained. And we can keep going until we find the best fit, which with no unexplained residual that suspiciously resembles human-induced warming, lies at about 0.8 degrees C of CO2-induced warming to date. Okay. And so the key take-home message from that is, the best explanation of the observed global mean surface temperature record is that carbon dioxide emissions from human activity have contributed about 80% of the observed warming since 1870. And that we can try and explain the observed warming with natural factors alone, but even allowing for any amount of amplification of the response to solar and volcanic activity leaves an unexplained residual that's very suspiciously well correlated with the expected response to human activity. So as I said, this hypothesis, null hypothesis, that humans have nothing to do with the rising temperature, can be comfortably rejected, and was decades ago, still is. In ECI, they still do this regularly, so you can go to the globalwarmingindex.org webpage and get an updated version of this kind of fit and attribution. You can see that updated as of September 2017, we've had about 1 degree of human-induced change.
Just to add, the extra 0.2 is other greenhouse gases, sort of net effect of other stuff. So the 80% CO2, and then if you include all the methane and all the other greenhouse gases, that's what takes it up to 1.
Yeah. And then I thought just to make it clear that we don't just do this with statistical fitting, which hasn't really involved any climate models, and that it's not only relevant for global mean temperature. I should include this figure from the IPCC, which basically shows a similar kind of thing. So the black lines here are observed trends in, the white ones are sea ice extent, the blue ones are upper ocean heat content, and the yellow ones are land surface temperature in various regions. And the blue bands in each one are climate models run with only natural forcings, and the pink bands are climate models run with natural and anthropogenic forcings. And you can see that almost without exception, it's only when you include the anthropogenic forcing alongside the natural forcings that you can explain the trends in various features of regional climate as well as this global mean temperature. Okay, so moving on to the future. What about future change, and what does science say we should do about it? Okay, so sort of, AKA, can we meet the goals of the Paris Climate Agreement? So I thought I'd put this in just because I'm sure it's something you've all seen, but I thought we should have some projection in here. So this is surface temperature projections from the IPCC report, which of course is your go-to resource for consensus view on all of these things. So this is the global average surface temperature change. There's a slightly different baseline of where 0 is, but you can see that for a kind of business as usual scenario, that's shown in the kind of pink here, the temperature change between now and the end of the century, it's up, 4 degrees here. You can see most likely 4 degrees, but quite a range. But even the lower parts of that range are comfortably above 2 degrees above pre-industrial. And I don't want to talk much about regional change because I know that's where you're going in the next few lectures into impacts. But I thought I would put these up. So this is in the kind of 2.6 scenario, so this kind of drastic action scenario, and the business as usual scenario, and it shows you that the world really is warming everywhere. Global means hide a lot of structure, but the world really is warming everywhere, and that climate change will mean different things to different people. And that 4 degrees, whilst undeniably important for everybody, will be more important for some than others. So the situation before the Paris meeting was that we were committed to limit the increase in global average temperature to 2 degrees C. That's a target that was bandied around, so it's interesting to think a bit about where that target comes from. And as far as I can tell, it was an economist actually at Yale called Wilhelm Nordhaus in 1977 first suggested that we might want to keep global mean temperature within a range not too far out of what's the normal range of variation within the climate system. And he can sort of define normal as not beyond something that we've experienced in the last few 100,000 years. Okay. And so suggested that if 1 degree is about where fluctuations sit, if we get up to 2 degrees, then we're comfortably out of anything that humans have experienced for a very long time. Okay, so that was the situation in terms of temperature targets before Paris, and key strategy for getting there was this idea of contraction and convergence. So the idea that whilst greenhouse gas emissions need to be scaled back, there should be a delay in the requirement for the developing world to do that, and that we should converge on a common amount of carbon emissions per person to make this an equitable process, but that we shouldn't do that too soon, 2050. Now there's a huge problem with this strategy, and that's that with contraction and convergence, the contraction convergence is fine so long as we converge on 0. There's no way we can stop temperature increasing if we don't stop emitting net carbon dioxide into the atmosphere. If we're not squirreling away as much as we're emitting, ultimately temperatures will continue to go up. And that's because of this graph, which shows that CO2-induced warming depends linearly on cumulative emissions. Okay, so here's our total cumulative emissions since the pre-industrial era, and here's the temperature anomaly relative to that period. Okay. And this is due, so we saw before that a doubling of CO2 leads to roughly the same change in radiative forcing. Okay. But there's a compensating effect, which Myles knows way more about than I do, about the airborne fraction, the amount of carbon that stays in the atmosphere versus being transferred into the ocean. And that they completely coincidentally compensate for each other and give us this linear trend. And so what's plotted on here from a whole range of climate model projections with a range of complexities of climate models, temperature change against cumulative emissions, and you can see whatever rate you make those emissions at, however long they go on for, we still seem to track up this same linear curve, but this is kind of an estimate of the uncertainty. So this has, there we go. So before I move on, so we've emitted about 560 or 70 gigatons of carbon already. You can see that if we emit another 500 or so, that takes us to a trillion tons of carbon, and that's consistent with a warming of about 2 degrees above pre-industrial. Okay, and so if we want to limit temperature increase to less than 2 degrees, then we need to emit less than a trillion tons. Is that straightforward, basically? And those are numbers you probably have heard before. Okay. And a few other points on here. If we postpone how long we get started on reducing emissions, it doesn't necessarily mean we're doomed to exceed 2 degrees, but it does mean that I'll have to work much harder to get there once we do get started. Okay, and we really do have to get down to zero if we want to stop temperatures increasing. So the the limit pre-Paris was a 2 degree, don't like the word target, 2 degree threshold. What happened in Paris? So that changed quite quickly with the suggestion that 1.5 degrees C might be better, and lots of people got on board with that. So these are two key parts of the Paris Climate Agreement. Article 2, this agreement aims to strengthen the global response to the threat of climate change by holding the increase in global average temperature to well below 2 degrees C, and to pursue efforts to limit the temperature increase to 1.5 degrees C. So this realisation that perhaps when we get to 2 degrees C, actually, especially for some parts of the world, things are already looking pretty bad. We might not want to let it get that far. And then Article 4, which arguably more important, might not look very important on a first read. So to achieve the long-term temperature goal, parties aim to undertake rapid reductions so as to achieve a balance between anthropogenic sources and removals of greenhouse gases in the second half of this century. There's two things buried in here. One is this undertake rapid reductions. Okay, so to achieve the long-term temperature goal, we're going to reduce carbon dioxide emissions. We're not going to try and change the incoming solar radiation with mirrors in space or aerosols injected into the upper atmosphere. We're not going to do any short-term expensive fixes. We're going to try and reduce our carbon dioxide emissions. And then implicit in this bottom part, this idea that we need to get to a net balance between sources and sinks of greenhouse gases if we're actually going to make any stable temperature work. And a suggestion of when we might need to do that by. So if you look at the carbon budget, if you like, for 1.5 degrees as estimated in the IPCC Fifth Assessment Report, so the 2013 report. Again, this is the same graph. You can see that to limit global temperature change to 1.5 degrees, then we need to be emitting no more than about 650, something like that, gigatons of carbon. Given we've already emitted 560 something, that doesn't leave us much. Our current emission rate is about 10 gigatons of carbon per year. Okay, so it doesn't leave us many years. However, there's some uncertainty in this figure, and you can see this large range. So where we are in here, we're in here somewhere now. There's a large range in the temperature change since the pre-industrial era, and actually we know much better than that what the temperature change has been since the pre-industrial era. So we can replot this figure relative to this decade, the 2010s. Okay, and we say, okay, we know we've had about 1 degree of warming. So if we want to stay within 1.5 degrees of pre-industrial, then we can't have more than about 0.5 or 0.6 above where we are now. Okay, and so if we reinterpret it in that framework, then we can see that we can have, so to get to about 0.6 above where we are now, we can have about 200 gigatons of carbon. Okay, so now we're talking about 20 years worth of current emissions at the current level. Okay. So can we do it? From the science side, Yes. Okay, we can do it. There's 20 years of current emissions. It doesn't have to take. If we started reducing them now and we reduce them linearly, right down to zero, then we have 40 years to get to zero. Okay, 40 years. If we start now and reduce them by the same amount each year, we'll get there. Another way of thinking about this: if we're already about a degree above pre-industrial, and we're warming about 0.22 degrees per decade. We have about 22 years before we cross 1.5. Okay, so 0.5 divided by 0.22 gives us 2.2 decades. So at the current rate, which again gives us 22 years at current emission rates, or 44 years to get our emissions to zero if we start reducing them immediately in a straight line down to zero. So yes, we can do it, but we really need to get started, I think is the upshot. So just to sum up then, so the most likely warming under a business as usual scenario is about 4 degrees C by 2100, with more warming after that. If we can get the emissions to fall to zero by about 2070, you can see that we do have the possibility of equilibrating temperatures at about 1.5 degrees above pre-industrial. It's not actually too late in any sense. People will tell you that we're committed to lots of future warming even if we stop emitting greenhouse gases today. But actually we're not committed to much. And I have to say, this is physics I don't really understand. Some compensation between the carbon cycle, right, Myles, and the ocean uptake of heat. But if we were to stop emitting greenhouse gases tomorrow, we wouldn't actually see much further temperature rise. So it's not too late. And then I'm not going to stray into policy, but just one last slide to say that the current pledges from the Paris Agreement are not sufficient. Here they are relative. So this is the CO2 emissions. Gigatons of carbon dioxide now is about a factor of 4 difference between gigatons of carbon dioxide and gigatons of carbon. And this is what's required to get us down well below 2 degrees C. You can see falling to zero by 2070, 2080. And this is the Paris pledges. So it's not enough, and it's only limited to 2030. It doesn't say what will happen beyond then. So more as a primer for what comes later in the course, really. And then some key points, really, just to make sure the take-home messages are all clear. So the first one here, greenhouse gases, they warm the planet by raising the level from which long-wave radiation escapes to space, and hence reducing the amount that's escaping, and causing an imbalance at the top of the atmosphere. The amount of imbalance, the radiative forcing, is relatively well pinned down, but the surface temperature response is not, and that's due to this myriad of complex feedbacks that goes on. Atmospheric levels of carbon dioxide at the moment are high, and they're changing incredibly fast in geological terms. And then, as we've seen, the best explanation by far of the observed global mean surface temperature record is that carbon dioxide emissions from human activity have, together with other human-related activities, have the root of the warming since 1870. This linear link between CO2-induced warming and cumulative emissions is crucial in how we think about mitigation strategies. And it is possible to meet the Paris 1.5 degree target if we can ramp emissions down to zero over the next few decades. And I'll leave it there.